Hello again. In this video, I'm going to work out another example where we use implicit differentiation. So let's look at example 3. So in example 3, we're supposed to find an equation of the line tangent to the curve given by this equation at the point 3, 2. Okay, so we found equations of tangent lines before in the past. And what we did is we found the slope of the tangent line by finding the derivative at that particular point that we're trying to find the tangent line, in this case at 3, 2. And we're going to do the same thing here. The thing that's different is to find the derivative in this case, dy dx, we're going to need to use implicit differentiation. We can't use explicit differentiation like we did in the past because we can't isolate the y in this case. Remember, when you use explicit differentiation, you have to isolate the y first. In this case, that's just not possible. We can still find the derivative, dy dx, using implicit differentiation. Okay, so let's do that first. We need to find the slope of the tangent line at this particular point. So we need the derivative, dy dx, and then we're going to evaluate that derivative at this particular point, 3, 2. Okay, so to find the derivative, we're going to use implicit differentiation. And so the first step in implicit differentiation is to take the derivative of both sides of the equation with respect to x. Okay, and of course on this left-hand side, we can find the derivative of each of these individually and then add and subtract them. Okay, and then the derivative of this constant, of course, is equal to 0. Okay, so let's just go through and find each of these derivatives. So this derivative here, of course, is just 2x using the power rule. Derivative here, we're going to have to use the product rule because we have the product of two functions here. So going through the product rule, we're going to take the first function, which is x, and multiply it by the derivative of the second function. Of course, the second function is y, and we're taking the derivative of it with respect to x. And so we're just going to get dy dx. And I'm just going to write that as y prime. Remember, that's another way of denoting the derivative. Okay, so the first times the derivative of the second plus the second, which is y, and then the derivative of the first with respect to x. So the derivative of x with respect to x is just 1. Okay, and now we've got to find this derivative. Now to find this derivative, we're actually going to have to use the chain rule, because this is really a composition of two functions. Y is a function of x, presumably. So you need to think of this y as being an inner function that depends on x. And it's being raised to this outer function, which is cubing it. And so remember, anytime you take the derivative of a composition of functions, you have to use the chain rule. Okay, to kind of reinforce this idea, let's just say, as an example, let's say y turns out to be equal to x squared plus 5x. Now, we don't know what y is equal to, but just as an example, suppose it's equal to this, right? It's some function of x. So let's say it's equal to that. And when you say y cubed, then you're getting this x squared plus 5x cubed. Now we're taking the derivative of that with respect to x. Now, if you're going to find the derivative of this with respect to x, it's pretty obvious now that you're going to have to use the chain rule because this is your inner function, x squared plus 5x, and it's being raised to the third power, which is your outer function. So the derivative here would be, the outer derivative would be 3x squared plus 5x raised to the second power. The 3 comes down and you subtract 1 from the power. That's your outer derivative, and then your inner derivative, of course, would be the derivative of this inner function. So you can use this to help you understand what the derivative of y cubed would be with respect to x, because this is simply y, right? This is equal to y here. So this is sort of saying 3y squared times dy dx, regardless of what y is. Okay, so the derivative of y cubed with respect to x is going to be 3y squared times dy dx from the chain rule, where this is the outer derivative and this one over here is the inner derivative. Okay, so you don't have to go through all this where I made up an example for what y is equal to. I just did that to kind of illustrate what would happen in this particular case when you find this derivative. What you can do is, once you really understand this, is you can view this as a composition of two functions, where y is the inner function and cubing it is the outer function. And so the outer derivative would simply be 3 comes down, and then you subtract 1 from the power. That's your outer derivative. And then you take the derivative of the inner function, which is y, but with respect to x. So you get dy dx. And I'm just going to write that as y prime. So it's the same thing that we had over here. Okay, and of course that's equal to 0. So now what we need to do is to solve for y prime and then evaluate that at this point 3, 2. And that will give us the slope of this tangent line at this particular point. Now normally, in order to solve for y prime, you would have to make sure that they're on the same side, all the y prime terms, and then all the ones that aren't y prime terms have to be on the other side. So in this case, you would have to subtract the 2x and the y to the right-hand side, and then you can factor the y prime out, then divide by whatever's left over, and that would give you y prime. But in this case, we don't really need to isolate y prime. What we can do is we can simply go ahead and plug in x is equal to 3 and y is equal to 2 into this equation. Because we're going to evaluate the derivative at this particular point, right? Which means we're going to plug a 3 in for x and a 2 in for y. You can actually do that immediately. You don't have to get y prime by itself first and then plug this point in. You could actually plug the point in first and then solve for y prime. And it's actually easier to plug in these numbers first. So that's what I'm going to do here, just because it's a little bit easier. So I'm going to plug in a 3 for any x that we have. So 3 there and a 3 here. And then I'm going to plug in a 2 for the y. So this is 2 minus 3 times 2 squared, because this is y, and y is equal to 2, and then times y prime. Okay, so this is going to give us 6 plus 3y prime plus 2 minus, and this course is going to give us 12 y prime. And then you can just add up like terms. So this is 6 plus 2 is 8, and then 3y prime minus 12y prime is minus 9y prime. Okay, and then let's just solve for y prime. Subtract the 8 over to the other side. And then divide both sides by negative 9. Okay, so y prime is 3/9. Now, technically, this is y prime evaluated at this particular point. So it might be, if you're more detailed about what this really means, we're actually plugging this number into the derivative and getting 8/9 out. Okay, so this is the slope of the tangent line to this particular curve right at this point 3, 2. And so now we just need to use the point slope formula for a line to get the equation of this particular tangent line. We know the slope of the line, the tangent line, is 8/9. And we know there's the point on the line. This particular point is on the tangent line, so we can plug that in for x1. x1 is 3, and y1 is 2. Okay, let's just clean this up and solve for y. So you can distribute the 8/9. Of course, you get 8/9x minus 24 over 9. And then we can add the 2 to the other side. Of course, you're going to need a common denominator over here. So instead of writing it as 2, let's multiply that 2 by 9 over 9. So it becomes 18 over 9, and that way we have a common denominator of 9. And so the equation of the tangent line is going to be 8/9 x. And then when you add these together, you get minus 24 plus 9, or minus 24 plus 18 is minus 6/9, which of course reduces to minus 2/3. Okay, so that's the equation of the tangent line to this curve at this particular point. Now let me just show you visually what's going on here. So if you graph this particular curve, the one that we were given, it looks like this. And notice this is not really a function because it doesn't pass the vertical line test. But nonetheless, the graph of this particular equation looks like this. Then right at this particular point, 3, 2, the equation of the tangent line, or actually the tangent line itself, at this point 3, 2 would look like this. You can kind of gauge as to whether the slope of this is 8/9. Certainly positive, and it appears to be close to 1, which 8/9 is close to 1. And then the y-intercept is certainly going to be a negative number down here, and it does appear like it might be close to negative 2/3, which is the y-intercept that we found. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.